Hi, my name is Jim Rautio. I'm President, CEO, and founder of Sonnet Software. I'm going to talk about the Sonnet Extreme Anisotropy Model for through-silicon vias. This is a very unusual model, and it is a proposed model. It has the potential of being able to accurately analyze extremely large arrays of through-silicon vias, a critical problem for high-speed packaging and high-frequency integrated circuits. I will start by talking about a baseline model for through-silicon vias. This will be effectively what we consider to be the correct answer. It takes a long time to analyze, but we want to see if the extreme anisotropy model using sidewall ports will provide the same answer as the baseline model. We'll take a look at data and output results, and then we will check the model using extreme anisotropy and via ports. This is the approach that will give us the maximum speed and allow us to analyze the largest arrays. After we demonstrate the via ports, we will estimate what the limits are on the maximum size of through-silicon via arrays that can be analyzed in a single EM analysis run. And we'll also show how to model the silicon oxide layer between the through-silicon via and bulk silicon. It insulates the through-silicon vias from the bulk silicon, and this is easily modeled by modifying the dielectric properties. Our baseline through-silicon via has some pretty extreme dimensions. I don't know if these can actually be fabricated today, but maybe someday. I picked the dimensions with the idea of making it extremely difficult to analyze. So we selected a cross-section, a square cross-section via, 1 micron on a side, very tiny. And we'll put the through-silicon vias very close together. We'll put a 2 micron gap between them. And we'll make them 100 microns long in copper, 1 micron on a side, and 100 microns long. That's a pretty extreme dimension. As I said, these dimensions are selected for analysis difficulty. This technique can be used for any dimensions and any cross-section. The particular dimensions I've chosen are simply to make it difficult to analyze. Because there is no ground in silicon, a mistake some designers will make is to think of the silicon as being a ground. That's a big mistake. There is no ground. We're always going to look at differential pairs for transmission lines. For our initial investigation, the through-silicon vias are modeled as being in ohmic contact with the bulk silicon with a conductivity of 8 Siemens per meter. And as I said, we can easily modify the dielectric properties to include the silicon dioxide, very thin silicon dioxide insulating layer that through-silicon vias usually have. Here's our baseline. This is the one we will analyze, and we will consider to be the correct answer. We analyze it as accurately as we can. We have the input over here between ports 1 and -1. It's a differential pair. You can see the port -1 is labeled there. And the output from the through-silicon via is through ports 2 and -2. I'm sorry, ports 3 and -3. The other line is ports 2 and -2 with output ports 4 and -4, and you can see the negative ports here. When you have a port 1 and -1, that means that's a differential pair. For every amp that goes into port 1, there will be 1 amp coming out of port -1. Over here on the left, we can see the port connecting lines. The port connecting lines will be de-embedded from the structure, so all we will have left after the EM analysis is the through-silicon vias by themselves. We have a differential pair on the left here, that's port 1, and port 2 over here, differential via on the right, and the port 2 ports go down to ports 4, the ports the 1 and -1 ports go down to the ports 3 and -3. A pair of coupled differential pairs. For the extreme anisotropy model, now this is where things get really strange. This is going to be a mind expanding experience. We'll have the silicon substrate set to epsilon relative equals 11.9 and sigma conductivity 8 Siemens per meter for the X and Y fields. X and Y fields are parallel to the substrate surface. However, epsilon relative will still be 11.9 for the vertical field. However, the conductivity, instead of the 8 Siemens per meter, we're going to have it over 1 million times higher conductivity. Conductivity of copper, 5.7 times 10 to the 7th Siemens per meter for all Z-directed fields. So any Z-directed field is going to think it's present in copper. X and Y-directed fields will think they're present in the silicon. We'll make connection to the top or bottom of the substrate. We'll generate Z-directed current in the Z-directed copper, simulating a through silicon via. We'll compare the results from this model, this extreme anisotropy model, to the baseline results. At first, you might think, how could this possibly work? Well, let's look at the numbers and see if it does, and then maybe we can understand why it's working. Here's the extreme anisotropy model. It looks almost the same top and bottom as the baseline model, but now there's nothing connecting. We don't see anything connecting the port 1 to port 3 or port 2 to port 4. They're not there. And that's because in this region we now have the anisotropic substrate. It has copper conductivity up and down and silicon horizontally. The feed lines come in 1 micron above the anisotropic silicon, and they have, over here on the left, you can see it better, they have short vias going down to the top of the silicon. At the top of the silicon, they connect to the silicon, the copper vertical conductivity, and this via will insert current all the way down through this anisotropic silicon all the way to the bottom. Now, again, this is extreme. How could this possibly work? Well, first let's see if it does work. And the question is, does this model give the same result as the baseline model? And, well, it almost does. S13, which is the through for the first line, looks pretty close, a little bit off. S11 has a fair amount of difference, maybe 25 versus 23 dB, something on that order. S12, backward crosstalk, almost identical. S14, forward crosstalk, almost identical. Well, that's encouraging. But let's see about this difference in S11, and that could be kind of important. We also have phases here. Phases are pretty much identical in all cases. A little bit of difference on S12 block backward crosstalk at low frequency, but the magnitudes of the S parameters at that low frequency are extremely small. So we've got excellent agreement demonstrating proof of concept. The largest difference, S11 magnitude, is about 3 dB. That's a little bothersome. We poked around on this a little bit, and we found out that the difference is because the anisotropic model is actually the S parameters for a via that's 0.1 micron larger. We're 1 micron in size, so the baseline is 1 micron in size. So if we analyze an anisotropic TSV model that is 0.9 microns in diameter or on a side, it should come up with about the same S parameters as the actual 1 micron diameter through silicon via. So we can test that hypothesis. And so we analyze the 0.9 micron diameter anisotropic through silicon via and compared it to the baseline. And now you can see S13 through, it is virtually identical. S11 reflect, identical. S12 backward crosstalk, identical. And way down here, 50 dB down, S14 forward crosstalk is virtually identical. This through silicon via, by the way, is slightly different from the one I showed before. In this case, we selected it to be a hollow square via with a side with walls are 0.1 micron in diameter and thickness. And here's phase. Again, phases track really well. A little bit off on S14 forward crosstalk, but remember that's 50 dB down. The kinds of outputs that are available, we can output an LRCG matrix. That is a multi-conductor transmission line. And we have the format here, L11, L21, L22, right there, nanohenries per meter. And R per unit length, C per unit length, G per unit length. This can be put directly in to Cadence Virtuoso and most any version of Spice. We also output nice little things like characteristic impedance. It's a 78 ohm. Remember, it's a coupled line, a pair of differential pairs. So the mode vectors, the first mode is odd mode. The second mode is even mode. You can see the numbers there, plus and plus, plus and minus. So odd mode is 78 ohms, even mode is 54 ohms. Characteristic impedance with imaginary parts. Remember, there's some loss here. So some important points. The anisotropic through silicon via model requires Sonnet's numerically exact Green's function. Green's function is the fancy way electromagnetics guys like to say coupling between subsections. Current on one subsection generates voltage on another. That's the Green's function. Sonnet calculates the Green's function, i.e. the coupling between subsections, exactly. And by exact I mean to full numerical precision. Only Sonnet does this. And Sonnet does it for uniaxial anisotropic substrates as well. And for the kind of extreme anisotropy we have here, remember the conductivity vertically is over 1 million times higher than the horizontal conductivity. Sonnet has no problem with that. It does it perfectly. And only Sonnet can do that. Because of the numerically exact Green's function, the anisotropic TSV model in Sonnet corresponds to meshing the through silicon via's length into an infinite number of infinitely short subsections along the length. The baseline we meshed into 256 cells along its length. The anisotropic model is effectively an infinite number of infinitely short subsections along the length of the through silicon via. And it does this with no cost, equivalent to an infinite number of subsections with no subsections at all. It actually makes the analysis faster because we don't need to subsection the vias in the substrate. The vias are taken into account by the anisotropy into conductivity. Analysis speed. On a 12-core 90 gigabyte machine, a high-end desktop machine, runs about $2,000–3,000 these days. Time per frequency. We needed 5 frequencies for analysis from 1 to 100 gigahertz, with results were automatically interpolated by Sonnet's adaptive band synthesis, which is the best electromagnetic analysis interpolation in the world by far. No one even comes close to it. Baseline analysis time for the baseline circuit now. That's one we mesh the heck out of to get as accurate results as possible. 1 hour and 45 minutes. For the anisotropic through silicon via, 7 seconds per frequency. The speed up is 6,307 times faster. 6,300 times faster using the anisotropic model. Now we don't need all those port connecting lines. If we use a via port excitation, which I'll show in a second, the port connecting lines don't need to be there, they don't need to be analyzed, and they don't need to be de-embedded. We just put via ports at the top and bottom and use that for the excitation. That's 0.2 seconds, 220,000 times faster. Well, what that means is we can do some very, very large arrays of through silicon vias, as I'll get to in a second. The box sidewall ports were used in the above examples, and I alluded to the via ports being able to do a faster analysis. Port connecting transmission lines were de-embedded from the data, leaving only through silicon vias. As I said, that takes extra analysis time to analyze the port connecting lines and then to de-embed them, both. It is also possible to use very small ports, very small via ports, directly at the tops and bottoms of the through silicon vias. We've tested this. It gives almost identical results to using the port connecting lines and de-embedding them. With via ports, we only need 2 subsections, provided it's 1 subsection for each port. That would require simple square or rectangular through silicon vias. So we can get down the subsection count to a minimum of 2 subsections for each through silicon via, 1 each for the input and output ports. So that means each differential pair with input and output would be four subsections. When using the extreme anisotropy model, as I mentioned, there are none, zero, nada, zero, nil, nothing for subsections required for the through silicon vias themselves. No matter how long they do need to be small compared to wavelength, short compared to wavelength. But other than that, no matter how long they are and no matter how many they are, we are going to be using 2 subsections per through silicon via, as few as. So 12 cores and 90 gigabytes, we can invert a matrix about 100,000 by 100,000, which means 100,000 subsections. 2 subsections per through silicon via. That means 50,000 through silicon vias in a single EM analysis. If we have 2 through silicon vias per differential pair, that means 25,000 differential pairs. We can output the S parameters, we can output the LRCG matrices, but these matrices are going to be big, 50,000 by 50,000. So the output matrix size will be the limiting factor. The EM analysis will not limit the size of through silicon vias that you can analyze using this technique. For the silicon oxide through silicon via insulation, insulates the through silicon via from the bulk silicon. We can model that, and it has to be passive and linear within that restriction. We can model the insulation very easily just by modifying the epsilon relative and the loss tangent for the effect of the silicon dioxide. This is a very easy calculation. Given the dimensions of the thickness of the silicon dioxide, and no problem including that. It's almost trivial, and it'll be a closed form calculation, and we'll investigate further as we proceed on this. In conclusion, the proposed Sonnet extreme anisotropic model of through silicon vias has been investigated and shown to work well in comparison with the benchmark, the baseline through silicon vias. It is possible to do extremely large arrays of through silicon vias, much larger than can be handled by SPICE or anything else that would need input would need a through silicon via model. The output can be in the form of S parameters. It can also be in the form of LRCG matrices, and the resulting S and LRGC matrix is the matrix size that can be handled by other analysis tools. SPICE and etc. is expected to be the main limitation to through silicon via array size. Thank you for your kind attention.